G'day, I'm Lance from Muddy Power. Back again, this time with the second episode in our series on professional off-highway vehicle design. Today, we're talking about crawlers. Once again, what I discuss is just general guidance. It is not advice. It's information you may seek to investigate further yourself. So let's get into it. I've talked about crawlers. I didn't say tracks. It's a crawler vehicle, it's not a tracked vehicle. When you work in different applications, you need to be careful with the terminology. A tracked vehicle can also be a railway vehicle, and you can get very confused if your client is talking about a railway vehicle and you think he's talking about a bulldozer. So, hence, it's a crawler, not a track. And what is it? Well, here's a good picture. So here's a good image we can use to describe a crawler. Obviously, there's tracks. In this case, made up of a chain with track shoes bolted onto it. Here we have a front idler. We have bottom idlers. We have a sprocket. And in some cases, there will be return idlers that carry the return strand of the track. That's a crawler. The other reason for avoiding the term track is vehicles have a track. It's a dimension across the vehicle from the center of tyres on one side to the center of the tyres on the other. If it's a crawler vehicle, it would be the center of the crawler on one side to the center of the crawler on the other. It gets very confusing if you're talking about the track of a track. So let's talk about the track of a crawler vehicle. That way, it's just a little bit clearer. Occasionally, the term wheelbase gets used. Normally, that is the distance between axles. For a crawler vehicle, that would be analogous to the center of the front idler to the center of the rear idler. It does get a little more complicated if the sprocket's elevated and so forth, but that's the general idea. Now, tracks have grouses, so let's have a look at them. This particular track has single grouses on each pad, and it's there to engage the ground and provide more tractive effort, or provide for more tractive effort. So it's the bit of the track that engages the ground. So why use crawlers? Well, they're really good at carrying heavy loads, much more than a tyre is. They offer low ground pressure, which in many cases is a big advantage. They work better in soft ground because of that low ground pressure. So you take them into places that you would not take a wheeled vehicle. The flip side of that is when they're bogged, they're really, really, really bogged. They also have a lot tighter turning. Perhaps they can pirouette. They'll certainly be able to turn on one track within certain limitations. From the military's point of view, they can cross trenches much easier than a wheeled vehicle. A wheeled vehicle can still do it, but you need lots of wheels. And they can climb obstacles. Again, that's a military requirement. you really don't want your bulldozer driver in a quarry climbing an obstacle. And they can be more stable under heavy loads, and that's why most excavators are tracked and not wheeled. So there's a variety of tracks available, all of different types for particularly different applications. Let's have a look at a few. So obviously you're familiar with this sort. This is the type of track that's on basically every dozer, excavator, etc. But you may not be familiar with rubber tracks. They're often now used on smaller excavators, but to me this is the progenitor of it all. This is a Haglund BV206 with a Skager 620-2 track. This is a rubber track. It's moulded in sections. It has a bit of RHS steel in each of the grouses, and it works very well. But works very well in cold conditions. Does have problems in hot areas of Australia, particularly on hot tarmac in hot ambience. But this has been widely used throughout the world, and there are a number of military derivatives of it now. And then we can look at something like this piston bully that's designed for use on snow. These are essentially conveyor belt tracks with cleats, steel cleats, bolted on. It's a much simpler track, but it's also not suited to really arduous duty off the snow. So the advantages of tracks, as we just said, is traction and the sharp turning. But there's some disadvantages too. They're heavy. There's lots of mass to accelerate and decelerate, and that's important if you're talking about a higher speed crawler vehicle. There's lots of external moving parts because you've got rollers, top and bottom often. You've certainly got front idlers, rear sprockets, etc. It's a lot more parts than is bolting on a wheel or a tyre. And as a customer's put it to me once, crawlers save up their pain. They're really good when they work, but when they're worn out, they cost a lot to fix. Suspension. Do you need suspension on your crawler? Maybe. Depends on the application. Certainly main battle tanks that are designed to go at relatively high speeds across all ground, yes. If you have a slow speed vehicle, probably no. Every possible suspension type has been invented, I think, in the past, particularly in World War II. All sorts of walking beams, equalising beams, self-steering, and on and on. Whatever vehicle you are designing for, that question has probably already been answered. One thing to remember about suspension is it's likely to affect track tension. Depending on which wheel is being pushed up, you can increase track tension or you can slacken the track. Obviously both are disadvantages or problems in particular situations. So looking at our basic crawler again, you can see there are lots of individual carry rollers, and that's because this track could run over a rock and all the weight could be on that roller. It can also be on the idler. So we need to decide how many of these carry rollers we need and how robust they need to be. Do we need return rollers? Well, maybe. That's a bit of a philosophical question. Looking at a typical German World War II vehicle, they use lots of wheels. inner and outer wheels. The Western powers didn't do it this way. But like the Russians, they used the top of these wheels as a return. So you may not need return rollers. When we look at slower speed applications, such as this continuous miner or underground coal mines, rollers weren't needed. There's a rear drive sprocket, there's a front idler, but there are no other rollers. It's a Bisalloy plate, and it's just a skid shoe, same on the top. There's no suspension fitted. The vehicle is about 60 tonne, and it basically flattens anything that would stick up in its way. Certainly you can see the size of it, the weight is obvious. This is a perfect application for tracks. You would not remotely consider wheels for this application. So let's look at the drive. Unusually, this particular German vehicle is driven at the front. And so is a Merkava. A Merkava is also driven at the front with an idler at the rear. For a main battle tank, that means the engine and transmission are in the front of the vehicle, offering more protection from penetrators for the crew. If a penetrator makes it through the armour, it then has to theoretically make it through the transmission and the engine as well before it gets to the crew. The counter-argument is that any penetrator hitting the engine disables the tank, and the crew may be forfeit anyway. But we consider what's happening with the drive force here. Driven at the front, going forward, the entire return strand is in high tension, running down here onto the ground. So the idler, in all forward drives, is seeing double the load, nearly double the load it needs to. If this was driven at the rear, this would be the high tension area only on the bottom, and this would just be return tension on the top, reducing the load on their front idler then. Again, it's a philosophical argument. I've seen vehicles driven from the front like this because this is where the slack is, or the slackest part of the track, and that allows the suspension in this area to work easier. I'm not going to get into that argument, that's the theory. So, now we've got a track. What do the shoes look like? And in particular, what do the grouses look like? And there's quite an array. So let's look at some. Back to our standard little picture. This is actually a high traction type arrangement with a single grouser. Of course, you can have flat tracks that don't have any grouser, and they would typically be used on heavy vehicles where you don't want them penetrating the surface. For example, a big crawler crane working on an oil refinery has probably got flat track shoes with no grouses, so it can roll around on the concrete, still spreading the load quite well, but not breaking the concrete or the tar. If we look at back at our little crawler, this has got a single grouser. Now that's a high traction arrangement, a single grouser, and it's generally fairly unusual. And here is a track shoe with two grouses, double grouser arrangement. Still allows access to bolts. This is for, well, to be honest, fairly rarely used. This is the one that is quite common, a triple bar grouser. Now the reason is it gives you reasonably good traction, but it tends not to penetrate. If you have to run it over a bit of concrete, or perhaps a bit of tar road as it's being unloaded from a truck. Um, Going in a straight line, a triple grouser won't ruin the pavement. Turning, yeah, it would, but if you're careful, you won't do much damage at all. In terms of military vehicles, like the Leopard 1, they have detachable grousers. So they can run around in the public without destroying roads in peacetime. They can put various types of grousers on, depending on the conditions, whether it's mud or snow, for example. There are also cross grousers, deliberately where the bars run an angle across the track chute, and that's designed to give lateral grip as well. So that if you're going across a hill, you can drive forward, but you're not sliding down the hill. And then there are even ice lugs, which are lugs added to single grousers to give, to allow it to pierce the ice. So you use the lugs to break through the ice and provide more traction. So why all of this different solutions for tracks and grousers? Well, it comes down to the friction. If you run a pad without a lug, without a grouser, you're going to get around, what's the number here, 0.6 coefficient of friction. If you go to a triple grouser, you'll get about 0.8. It's a 30% improvement just for changing grousers. But if you go to a single grouser, you'll get 1 or 1.1. And 1.1 means you're able to exert more tractive effort than the vehicle weighs. So that's a lot of traction, but don't go anywhere near a public road with that. So this example is a fairly conventional track. There are, again, a multitude of varieties. This is a chain with bolted on track shoes. Doesn't have to be that way. There are lots of applications where track shoes are cast and then machined to take pins. There's a variety of pin arrangements from bushed to lubricated and so forth. If you are designing for military, that will lead you down one particular path of track. If you're designing for construction equipment, that will lead you down this direction. The decision will already be made for you in most cases. But the point here is there's such a wide variety of proven track designs that you can pick from. And then there's the weird ones. This vehicle is a World War II era buffalo or alligator, depending on whether you're American or British. It's an amphibian. This one happens to have a howitzer placed in the back of it. Various versions, but the tracks are very special because they have the water scoops fitted. The only propulsion for this vehicle in the water was the tracks, so they used them for double duty, by boiling water scoops into the track pads. The problem here is, again, don't take it near an established public road, but it's a solution for an amphibian vehicle that worked quite well across many different series of these vehicles. So we're back to the whiteboard, and I'm going to draw a plan view of a pair of crawlers. And we're going to talk about steering crawlers. So there's a basic undercarriage. Most people, when they talk about steering or turning a crawler vehicle, talk about moving it around a dead track. So let's say this track is stationary. There, I've used the wrong term. This crawler is stationary. This crawler moves. So we're going to get a radius of turn like that. And that's often sufficient. But if you want a really manoeuvrable vehicle, you want to be able to rotate it there, about that centre. In other words, one track forward, one track backwards. And how do you determine that? How do you know that your vehicle will be able to turn at all, let alone pirouette? Generally speaking, if it will turn on one track, on a dead track, then it will turn in a pirouette. But there are a couple of ways that we've been experienced with that will tell you mathematically whether you can cover it or not. So one method I'm familiar with is the CAT method. And they actually use a turnability ratio, TR. And depending on what factor that generates, it'll tell you how the vehicle will steer. So their TR is the drawbar pull by the track. This is where we get a fused track of vehicle over the GVM by, I'll call it the wheelbase, front to rear centres of the idler and drive sprocket. This terminology should probably be tractive effort, not drawbar pull, but we'll cover that in another video. And they say that if you've got 0.4 as a turnability ratio, you turn about in a 5-foot radius. If you've got a turnability ratio of 0.3, it's about 20 feet. From that, we can determine the necessary tractive effort per track to be able to turn the vehicle. Another approach we've seen is from Intertrack. They do it slightly differently. So they say the tractive effort per track has got to be U by G by A over 4E. Doesn't make much sense like that, does it? This one is actually mu, coefficient of friction. 0.6 for flat, 0.8 for triple grouses, and 1 to 1.1 for single. Oh, there we go. Back on the screen. G is a GVM. A is the wheelbase. And E is the track of the vehicle. So to be able to turn, you know what tracks, pads are using, the weight of the vehicle, the length of the track, and the track of the vehicle, you can calculate what tractive effort that track has got to create. Coming back to a sketch of an undercarriage. Coming up with tractive effort and having the tractive effort is important. But whenever you turn a crawler vehicle, let's say you turn it that way, this bit of track, crawler is going that way, this bit of crawler is going the other way. And that means, particularly in loose conditions, you're going to get a build-up of material beside the track, also in here and again on the other side. This can often be the limiting case. You might find you sink into the surface, you might find you damage the track, or you put so much material in here you have other problems. This is something you need to consider. The longer the track, the longer the crawler, the bigger the issue. It is what it is, but it's something mainly operators, but also designers, should be aware of. So when we come to something like a main battle tank, that might have a hole here with a thing out front, and in under here are the crawlers. Because it's running at very high speed, it's a difficult and complex matter to steer it. Essentially what happens is that one track is geared to the other track. It's much more complex than that, but essentially you're doing the gearing, and in some cases, to me, using the momentum of the vehicle to steer it, because you've suddenly geared one track down, so there's a bit of a momentum throw to turn the vehicle. You slow this track down, it's going to turn that way, and in practice, in military vehicles, mostly it's also the ratio at which you can steer is also dependent upon the gear ratio you're in. So you can't do a tight turn in third gear. You have to be in first gear. That's not always the case, but it's commonly the case. So that's a brief introduction to some of the background to using tracks, or crawlers as I should be calling them. Crawlers are great things, they're magic in the right application, but they bring with them some complexities as well. You need to make sure that you've covered all bases, make sure you've covered things like ground pressures, grouses, steering, tractive effort. Be sure of it, and then you can move confidently on to design the rest of the vehicle.